folium of Descartes is an algebraic curve carved out by a certain equation. By which equation? This equation, x cubed plus y cubed minus 3axy equals 0. It's the points in the plane that satisfy this equation. So what's a folium? Well, folium is just a Latin word for leaf. You know, the sorts of things that grow on trees. So where's the leaf? Well, here's the leaf. I've plotted the points in the plane that satisfy x cubed plus y cubed minus 9xy equals 0. And this is the curve that I get, and you can see it looks kind of like a leaf. This is not the graph of a function. It's really a relation. X cubed plus y cubed minus 9xy is a polynomial in two variables, in both x and y, in both. I can't solve for x in terms of y. Look, this graph fails the vertical line test. For a given value of x, there's potentially multiple values of y which will satisfy this equation. So what's the point of all this? Well, once upon a time, Descartes challenged Fermat to find the tangent line to this folium. And Descartes couldn't do it, but Fermat could. And now, so can you. And you can do it with implicit differentiation. So let's use implicit differentiation on this, thinking of y secretly as a function of x. So the derivative of x cubed is 3x squared. The derivative of y cubed, well, that's 3y squared times dy dx. That's really the chain rule in action. Minus, now it's got to differentiate this. It'll be 9 times the derivative of x, which is 1, y, minus 9x times the derivative of y, which is dy dx, and that's equal to 0. All right, now I can rearrange this. The things with the dy dx and the things without the dy dx can be gathered together. So 3x squared minus 9y plus, and the things with the dy dx term, 3y squared minus 9x dy dx equals 0. Now I'm going to subtract this from both sides. So I'll have 3y squared minus 9x times dy dx equals minus 3x squared plus 9y. And I'm going to divide both sides by this. So I'll have dy dx equals minus 3x squared plus 9y over 3y squared minus 9x. And note that we're calculating dy dx, but the answer involves both x and y. And you can see it's really working. I can pick a point like the point 4, 2 and ask what's the slope of the tangent line to the curve through the point 4, 2. And if we go back to our calculation, the derivative of y with respect to x, if I plug in 4 for x and 2 for y, I get that the slope of the tangent line to that point is 5/4. And yeah, that doesn't look terribly far off. I mean, this graph is a little bit stretched, but you know, that line looks like, yeah, it could very well have slope 5/4. Problems like this one, which once stumped the smartest people on earth, can now be answered by you, by me, by lots and lots of people. Right? Calculus is part of a human tradition of making not just impossible things possible, but things that were once really hard much easier. Well, in any case, there's plenty more questions that you can just ask about different kinds of curves besides this folium of Descartes. You can write down some polynomial with x's and y's, like y squared minus x cubed minus 3x squared equals 0. And then you can ask about the points, the x comma y's, that satisfy this equation. And if you want to know the slope of the tangent line, use implicit differentiation. The trick is just to use the chain rule and to treat y as a function of x.